Lesson 2.1.2. How are some functions like a day at the beach? Okay, well, we're going to talk here a little bit about shifting functions, a little review there, function transformations, and I think we throw in some piecewise functions there as well. So you would have this resource page with you already at home, so you can take that out, and we'll be using that for this lesson. So how is a transformation of P? How is Q a transformation of P of X? So if you're looking at that, these two equations written here, we have P of X is defined as this parabola, for lack of a better way to say it right now. This is just a parabola that we will graph. And Q of X is P shifted to the left 2. All right, it's a horizontal shift because it's inside the function, the parentheses there. The plus 2 is affecting the X. It says use the graph of P of X to sketch the graph of Q of X on grid A of your resource page. Find an expression in terms of X for Q of X. So let's go to the resource page here. And I think what's pictured there is P of X. And we're trying to graph Q of X. So there's some important points here. I know that the vertex would be one of those points. However, it doesn't fall on a grid line. So I'm not going to use the vertex to shift this graph. I instead am going to dot some of these other points here that do fall on grid lines. Makes it a little bit easier on myself. And I'm going to shift all of those to the left 2, because that was my horizontal shift as defined in the problem. So if I move each of these points to the left 2, I will get my new graph. The vertex, I just got to estimate a little bit. It's going to be a little bit below those two. And I go ahead and draw that graph on grid A. Okay. And let's sort of look back here at what my instructions were. Find an expression in terms of X for Q of X. So the important part here is I'm going to write Q using function P. So I know Q is P moved to the left 2. So Q of X is going to equal X plus 2 squared plus X plus 2 minus 2. All I did here was substitute my shift of X plus 2 in place of the X's from my original function. Now I could simplify that if I wanted to, because obviously this plus 2 and this minus 2 would cancel each other out. I could square this binomial, but I personally wouldn't do that because I like this version of it. It shows me what the shifts are staring me in the face. So leave it there. Consider graphing form still. Okay, let's see what else we got. The graph of f of x is shown to the right and on grid B of the resource page. Use the graph of f of x to sketch the graph of g of x, which is going to be f. Move to the, let's write these out. Little review here. Move to the right 1 and moved up 3. It's 2 shifts happening here at the same time. So I'm going to go back to my original graph. I'm going to do my 2 shifts. And those shifts were right 1. Again, define those points ahead of time. So my 2 vertices here are grid lines. My x-intercepts are perfect too. So I'm going to move them right 1 and up 3. So I can do that simultaneous. Right 1, up 3. Right 1, up 3. Each point gets moved like that. I even think my y-intercept there is a good one. Okay, and that gives me enough points to be able to draw this graph here with a fair amount of accuracy. Right 1 up 3. Now it says describe the transformations. Right 1 up 3. So we're good. Most of us are comfortable when shifting parent graphs as we did on A and B, which is review of algebra 2. But do piecewise functions have the same properties? Absolutely. When you shift them. So sketch your graph of f of x on grid C. So here they're giving us a piecewise function, x squared when x is less than 2, x plus 2 when x is greater than or equal to 2. All right, so let me go back here to grid C. So it's x squared when x is less than 2, and x plus 2 when x is greater than or equal to 2. So I'm going to go ahead and draw those. So x squared when x is less than 2. Again, this looks the same as what we've done already. They're really going easy on you here as far as this is concerned. So let's see, less than, so 0, 0, over 1 up 1, over 2 up 4, and that's an open circle. Draw my left side there, and that's a parabola. Okay, and then it's going to be x plus 2 when x is greater than 2, so over 2, and then let's see here, it's up 2, so 1, 2, my slope is 1, up 1, over 1, up 1, over 1. Just so happens this one fills in that dot. Okay, so this would be a continuous piecewise function that's made up of a parabola and a linear. Now we go back to our problem here, which says if that's f of x, okay, then let h of x be f of x minus 1. So that means we're going to take our function f, our piecewise function, we're going to move it to the right 1. It says use a different color, so let's use red. It works the same as any other graph you've ever have shifted in the past. So again, we're going to move all these points to the right 1. So the points we just plotted all get moved to right 1. That means our domain point gets moved to the right 1 as well. And we draw those two pieces, parabola and line, shifted to the right 1. Nothing else changed, just to the right 1. And let's go back here to our problem. For the function f of x, that transition point occurred at 2 originally. What does the transition point occur for h of x? It would occur at 3. If you're at 2 and you move to the right 1 on a number line, you end up at 3. It's tough math here. Find the piecewise function for h, write that function in the space provided on the resource page. So what we're going to do is we're going to take this function here, our original one, and we're going to apply our shift to it. So let's take a look at what that may look like. So the x squared is easy because now it's just going to be x minus 1 squared. All we're doing is including that horizontal shift in there. Okay, the x plus 2, and again, this can work easy if you wanted to. It's going to be x minus 1. Oh, I guess I can't write over top of that. It's going to be x minus 1 plus 2. Again, the x minus 1 gets substituted in place of the original x. That's it. Nothing else needs to, you don't need to worry about nothing else. Okay, now you could simplify that. X minus 1 plus 2 obviously is x plus 1. That's okay. And then we need to rewrite our domain. Sorry, these are backwards. I can't write over top of my ticker tape or it messes it up. And again, that new transition point is at 3, so that's why the domain changes to 3. So let's look here at problem D. It says using f of x from the original one, now we're going to define k, a new piecewise, which would be to the left 2 and down 3. So now we're going to take that original piecewise function f from the 2 problems ago, and we're going to move it left 2 down 3. Let's sketch that. And we're going to find the equation for it. Okay, so remembering there that our original function f of x, so before we leave this page, let's talk about the equation, because you can get the equation without even doing the graph first. So we have f of x defined as x squared when x is less than 2, and x plus 2 when x is greater than or equal to 2. Okay, so let's define k of x, and it's going to look a lot the same, except we're going to insert these shifts. So we're going to have an x plus 2 squared, and then a minus 3 outside of those parentheses. And then we're going to have an x plus 2, whoops, typo, x plus 2 inside parentheses, minus 3, plus 2. We don't want to forget about the plus 2 from the original. We don't want to forget about the minus 3 from the shift. Now obviously there's some simplifications that can happen there, and that's okay, go for it. Now, when we talk about how our domain has changed, we're talking about domain. Domain is a horizontal value. It's an x value. There's only one shift there that will change the domain, and that is the horizontal shift. Horizontal shift here is left 2. So if you're standing at 2 and you go left 2, you're going to end up at 0. Okay, if you're standing here and you move left 2, you're going to end up at 0. The vertical shift does not impact that domain at all. That is an important point to remember. So please make a special note of that. Only the horizontal shift impacts that domain when you're shifting a piecewise function. That's going to come up again later in the chapter with area under the curve, where only horizontal shifts where only horizontal vertical shifts, the difference between those two and what impacts area in the curve and what doesn't. Okay, so if I were to simplify this, though, I would end up saying, I would leave the parabola the same because it just looks like graphing form. And a linear, I would actually simplify this. So I'd have a -1 here and a +2, so I'd end up with x plus 1. Just makes it look a little nicer. Now, to graph that, again, same thing. Take this original one here, the one in blue. We're going to move it left 2 and down 3. So each of those points, left 2, down 3. Okay, left 2, down 3. All right, I could fill some of these other ones in. Parabola section, linear section. A little bit tougher problem, but you know we're building here. We're moving on. Now the second phase of this lesson here deals with a new topic called period of a function, and that's what we're going to take a look at next. So periodic function is a function whose graph repeats identically over and over, and it follows a pattern basically from left to right. The graph picture below is periodic. You have never graphed these before, so this will be your first time taking a look at periodic functions. Periodic functions such as this one is shifted horizontally by certain values. The graph does not appear to change. For the graph below, what horizontal shift would you have to have? Now that's as simple as taking a look at this graph and noticing here on the resource page that this point and this point coincide. Therefore, if I shifted this point that far, okay, the graph would stay the same. And what distance is that? That distance is 5. Okay. Use the resource page to investigate the periodic function. Write your notes and comments on the page. Save it for later. We're going to go over that when you come back to class. What's the domain and range? So this first periodic function is one we're looking at. Domain is all real numbers, because that arrow is going on forever and that arrow is going on forever. Okay. The range here is a little different. We assume the pattern continues. All right. We assume the pattern continues. Therefore, the range, the highest it can go is 4. The lowest it can go is 2, so the range will reflect that. Okay. What else we have here? What is the y-intercept? Label on the resource page. Okay, so the y-intercept is here. Now that point's not labeled, but we know it's going to be a 0 for the x, because every y-intercept has a 0 for the x. And we know for the y value here, that's a lowest point, it's a minimum, therefore all those y values are at 2. So you just have to use some reasoning skills there to determine that. Oops, wrong way. Are there any asymptotes or symmetry? No asymptotes, but we do have symmetry. I don't know how much you guys go over this in geometry, but I'm pretty sure we call it translational symmetry. All right, it's a slide symmetry. You can take that graph, you can slide it left or right, and it would match up with itself. Last, does the function belong to any parent families that you've studied in the past? No. Does not. I mean, you could define it with a piecewise function using a linear piece for this section and then another linear piece for this section, but to get those pieces to repeat one another and continuously we don't know how to do that yet. So now periodic functions have what we call periodicity, which simply means they repeat at regular intervals. Many things you're familiar with also have this quality. Clocks, for instance, repeat every 12 hours. Unless you're on military time, that's 24 hours. So on and so forth there. For the function above, we can say a period was 5. That was a previous function we just looked at. Looking at the graph of f of x, knowing that the period is 5, you can answer the following questions. Is f of 2 equal to f of 17? Why or why not? Illustrate this reasoning on your graph. So if we look at that graph, what's f of 17 going to be? So if we know f of 2, okay, happens somewhere in here. All right, because 2, 3, 4, 5, and they're telling us that value, we don't even know the y value, so it doesn't even matter what the y value is. So here at f of 2, will that be equal to f of 17? Well, what you do is you look at this section, all right, throughout the graph. And what would that value be? And what's the distance between these points? We already said that distance is 5. So f of 2 This will be f of 7. This will be f of 12. And this will be f of, you got it, 17. All right, so yes, they would be equal. Basically, you're drawing a horizontal line there to show that they would be equal. The other thing you could do, it's real simple, is take 17 minus 2, and you get 15. Is that number divisible by our period? Which in this case, the period's 5. Answer is yes, it'd be 3 periods later. All right, is f of x equal to f of x plus 5? Yes. All right, because it's a horizontal shift of 5. So you're just sliding at 5. Anytime you're sliding at 5, 10, 15, 20 increments of 5, it's always going to be equal. On the resource, on the resource page, label the points in the graph where it reaches its maximum minimums. By inspecting the graph, estimate the solutions to the equation. Okay, if x is 3, from negative 4 to 16, plot the solutions on your graph. How many solutions are there? So here it says max and mins, label those, which you can all do. You know, they just keep repeating itself. So 10, 2, 15, 2, okay. Here it goes 1, 6, and I'll go 11, 4, then I'll go 15, or not 15, excuse me. It's growing by 5, so it's going to go 16, 4, so forth. And then the second part of that asks us to determine where f of x equals 3. So that's a guesstimate. All right, if the lowest value here is 2 and the highest value is 4, 3 is going to happen right in the middle of that. And it's asking us to determine what those x values are, where that is true. Okay, so it looks to me like this happens halfway between 0 and 1, which would be 0.5. And then each section there, not the next one, but the one that's on the steeper branch, the positive branch, is going to be 5 away. So that'd be 5.5. And that one's going to be 5 away, so that's 10.5, so forth. Now this one is different. Okay, that's on the downhill side of things. And see, we have 1 to 5, okay, for our x value. So 1, 2, 3, 4, 5. So that means that's going to be 4, f of 4. 5 more than that is going to be 9. Whoops. Whoa. 5 more, that's going to be 9. 5 more than that, it's going to be 14, etc. Again, if you have questions about that, we could talk about that when you come to class. Maybe watch that again, wind it back, and sort of play it through your head again. All right, next, g of x is periodic function shown to the right, which is also on your resource page. What's the period of g of x? So again, you're trying to figure out what that shortest distance is before the graph starts repeating itself. And again, you can use maximum values, minimum values, or any other important points in the graph. So it looks to me as though, let's just say, for instance, I started here at this maximum. How far until that graph reaches that maximum again? And that will be right here. So what is the distance there between 9 and 2? 7. So our period here is 7. So every 7 units is going to repeat itself. Name 6 values for x when y is 1. So we go to where y is 1. That's this line right here. And we got to find 6 x values when y is 1. Okay, so it looks to me like y is 1 right here, and that would be half. So 0.5 is one of those x values. Now, again, I could add 7 to that and get the rest of my values that I need, because that's how periodicity works. It just keeps adding that period, okay? Or I could come over here and determine this one, which is halfway between 4 and 5, so that's 4.5. So I could use 4.5 and just keep adding 7 to that, 11.5, 18.5. But you'll notice, though, there's not a common difference between the two groups, okay, because they're not equidistant apart. From this point to this point is different from this point back to this point. So you do have to be a little bit careful there. What is g of 53? So if we were to extend this pattern out to 53 on the x-axis, where would, or what would the y value be? What would the graph look like at that particular place? A couple of different ways you can go about this. I'm going to show you a shortcut. What I typically tell people to do is take 53 divided by 7. All right, so a little long division here. 7 times 7 is 49. We subtract, we get 4. Okay, so what that means is we're going to go 7 whole sections of this graph. 7 whole sections. Okay, and this number here, typically when you were learning how to divide in elementary school, we call that the remainder. All right, so that tells us where we end up on that last section. We end up at 4. So we come over here to 4, come up here, and we see the y value will be 2. Okay? It's all about the remainder there. And that's it for that lesson. Have a good night.